Today we speedrun real normal operators and the real spectral theorem. Complex vector spaces give diagonal matrices. Real vector spaces give blocks. Because apparently two dimensions wanted their own subplot. Over the complex numbers, we already proved the clean version. Normal means t commutes with t star. And over C, that is exactly the condition for orthonormal diagonalization. That diagonal matrix is why the complex theory feels civilized. Suspicious, but civilized. Over the real numbers, normal does not guarantee real eigenvectors. This is the 90-degree rotation of the plane. It is normal, but no non-zero real vector points in the same direction after rotation. The missing eigenvalues are hiding in C, I and negative I. Real spaces do not get to use them directly. Naturally. This causes paperwork. The diagonal theorem still works over R if we use self-adjoint operators, not all normal operators. So the real diagonal story is self-adjoint if and only if there is an orthonormal eigenbasis. The proof idea is induction. Find one eigenvector. Show its orthogonal complement is invariant. Then repeat. Not glamorous, but functional. Which is more than we can say for many things. Now for the full real normal operator theorem. Since diagonalization fails, the best replacement is block diagonalization. Every block is either 1 by 1, meaning an honest real eigenvalue, or 2 by 2, meaning a real plane behaving like one complex eigenvalue pair. The block diagonal matrix is the real substitute for a diagonal matrix. It is less pretty, because reality enjoys being difficult. The 2 by 2 block is not random decoration. It is complex multiplication disguised as real linear algebra. The matrix sends the real coordinate pair x, y exactly like multiplication by a plus bi. Sends x plus iy. So a two-dimensional real block is one complex eigenvalue and its conjugate. Packed into a real plane like luggage nobody asked to carry. Over C. This would split into two eigenvectors. Over R. It stays as one two-dimensional invariant plane. We are not doing every detail, but the proof has a clean skeleton. The real replacement for eigenvectors is invariant subspaces of dimension 1 or 2. One-dimensional pieces are easy. Two-dimensional pieces are the price of refusing complex numbers. That invariant orthogonal complement is what lets the induction produce a block diagonal matrix, instead of a chaotic rectangular soup. The only new local object is a two-dimensional real normal operator that is not self-adjoint. Start with any orthonormal basis of the two-dimensional piece, and write the matrix with 4 real entries. Normality says the length of t(E1) equals the length of t star E1. So b squared equals c squared. If c equaled b, the matrix would be symmetric, hence self-adjoint. In the non-self-adjoint case, c must be negative b. Then multiplying t star and t star t forces the other diagonal entry to equal a. After changing orientation if needed, b is positive. Now the full theorem is assembled by induction on the dimension. Choose an invariant subspace U of dimension 1 or 2. Normality lets the orthogonal complement stay invariant too. Then one piece contributes one block. And the orthogonal complement is handled recursively. Congratulations! Induction has entered with a clipboard. Here is the whole story compressed into one comparison. Complex normal means diagonal. Real self-adjoint means diagonal. Real normal means 1 by 1 and 2 by 2 blocks. Next, positive operators. Fortunately, positive operators are self-adjoint, so we mostly get to use the diagonal theorem and pretend the rotation blocks took a coffee break.